All right, this is Mr. Kranz here. This is my first view of the 2020 AP FRQs. Got your formula sheets, same as last year. Nice. First one, here we go. Ooh, scatter plot. Biologist, data on length in millimeters, mass in grams for 11 bullfrogs. Data plot are shown. Describe the relationship between mass and length in context. So I'm going direction, unusual, form, and strength. Strong, positive, linear relationship between the length in millimeters of a bullfrog and its mass in grams. Maybe this one unusual point is a rather long bullfrog that had a light weight. Okay. Part two for the data. The biologist calculated the LSRL, least squares regression line. Identify, interpret the slope. The slope is 6.086, so I always do a delta y over delta x predicted. So I would say for each additional millimeter of length, the mass in grams of a bullfrog is predicted to increase by 6.086 grams. All right. Make sure you use that word predicted. You're in good shape. Interpret the coefficient of determination. R squared equals 81.9%. In context, 81.9% of the variability or the variation in mass in bullfrogs is accounted for by using length to predict its mass. All right. And then from plot 2, consider the residuals of the 11 bullfrogs based on the plot. Approximately what is the length and mass of the bullfrog with the largest absolute value residual? This one looks like it's the farthest. And if I plugged in about 162, well, I don't even need. So it says approximately what is the value. So this one looks like we're at about 430 and down here to about 355. And if you just do 430 minus or observed minus predicted, 355 minus 430, because it says what's the value, length and mass of the bullfrog with the largest residual. So I would say his length is about 162 or 3, and its mass is 355, we'll say, or 360. Okay. Does the least squares regression line overestimate or underestimate the mass of that bullfrog? So the estimate is over. Okay, it overestimates the mass of this bullfrog because that's his actual weight. That's estimate is over. Okay, right here, dermatologist conduct an experiment to investigate the effectiveness of new drug to treat acne. The dermatologist recruited 36 pairs of identical twins. Sounds like it's going to be matched pairs. Each person in the experiment has acne. Each person will receive either the new or the placebo. After each person in the experiment uses the new drug or placebo for 2 weeks, dermatologists will evaluate the improvement in acne severity for each person. Treatments. The treatments are the drug or the placebo. The experimental units are the individuals, the identical twins. The response variable is the improvement in severity of acne. Okay, it has severity similar to that beforehand. However, the severity of acne differs from one twin pair to another. For the dermatologist experiment, describe a statistical advantage of using matched pairs design. Well, it basically accounts for the variability between those, the differences in severity of acne from one twin pair to the other, because by doing matched pairs, since the two twins have similar acne, then if they end up with different acne afterwards, we're just looking at which one has had a greater improvement rather than just lumping in all this variability, right? If you just look at all the twins that were really, really spread out, then you get all that variability. But instead, you have two twins that started out close, and therefore there's a delta for each of them. And these two started off close, and there's a delta for each of them, hopefully getting better. Okay, so it reduces the variability is what I would be looking for in that answer. Describe how the treatments can be randomly assigned. So here, match pairs design, in which twins are paired. So in match pairs, you have a lot of options. Typically, I say put the names into a hat, but if it's match pairs, right, you already have the twins. So you just take the first twin and you flip a coin. If it's heads, they go into treatment 1, and the twin number 2 goes into treatment 2, or vice versa. If it's tails, then twin A goes to treatment 2, and twin B goes to treatment 1. Okay, something where there's randomness, and then you say for each pair, they get assigned. For each pair, they get assigned, okay? Question 3. A machine at a manufacturing company is programmed to fill shampoo bottles such that the amount of shampoo in each bottle is normally distributed. I'd sketch my normal curve right now. Mean 0.6, go to 0.04 to the left and right, okay? Random variable A that is inserted into a bottle by the filling machine. Underfilled, less than 0.5, determine the probability. So this one, you're shading on that lower half. We're exactly 2.5 standard deviations below. So you could look up a z-score, -2.5. You can do normal CDF, and you're in good shape. After the bottles were filled, they are placed in boxes of 10 bottles per box. Now, this is a sample, okay? After the bottles are placed in the boxes, several boxes are placed into a crate. The manufacturing company's contract with the beauty supply warehouse states that one box will be randomly selected. If 2 or more bottles in the selected box are underfilled, the entire crate will be rejected. So there are 10 boxes or 10 bottles, and if 2 or more, so we're looking at a binomial probability, okay, because you can have up to 10 failures, okay, or 10 that are underfilled. We're looking for if 2 or more are underfilled. So you want to do 1 minus the binom CDF of 1 or fewer, okay? We're using the probability had up here in part A, in part B, okay? Assume the amounts of shampoos are independent. Define the random variable interest for the warehouse manager and state how the random variable is distributed, okay? So, like I said, it's a binomial random variable. It is distributed, centered at the n times p, which is 10 times whatever your probability was right there. You could talk about the standard deviation, square root of NPQ, but it's a binomial distribution, okay? And determine the probability. Once again, that's that 1 minus binom PDF. All right, to reduce the number of crates rejected, the manufacturing company considered adjusting the programming so that in each bottle it's normally distributed 0.56, standard deviation of 0.03. Would you recommend they use the original programming or the adjusted? Well, here it's 2 standard deviations below the mean. It's still normally distributed. The other one was only 2.5 standard deviations below the mean. So I like the OG original programming, okay? Number 4, survey conducted by a national research center. 920 teenagers. How often they use a video streaming device. For the sample, 59% said they use it. Construct and interpret a 95% confidence interval. Okay, so it tells you confidence interval. Sweet. Proportion of all teenagers who would respond that they use a video streaming service all day. So here I would use panic. The parameter is the true proportion of teenagers in the United States who would respond they use a video streaming service all day. And then my assumptions and conditions, it says that it's a random sample. You're going to have 59%, so NP and NQ, 59% times 920 and 41% times 920 are both at least 10. So we have large counts, and so we have normal distribution, and it's reasonable to assume that these teenagers in this random sample are independent of one another, okay? And then I would name it. So we're doing a 95% confidence interval for proportions, okay? And then make my interval. And I would use this 0.59 plus or minus this 1.96 because it's a 95% confidence interval. We always get to use Z with proportions times the square root of P times Q. So 0.59 times 0.41 over N, 920. And that would get me my confidence interval. And then I'd say we're 95% confident that the true proportion of all teenagers in the United States who would respond that they use a video streaming service every day is between whatever the min and max of that interval is. And I would be done, okay? Panic is there to get you full credit on a question like that. Do the sample data provide convincing evidence that the proportion who would respond is not 0.5, okay? So nice thing about is not 0.5, a two-way test is equal in logic to whether or not a 95% confidence interval captures it. So this is an alpha 0.05. If 0.5 is in that interval we got up above, which I haven't done the math, then I would say no, the data do not provide sufficient evidence of that because 0.5 is in the interval. Or if 0.5 is not in the interval, you could say, yes, there is less than a 5% chance that you would be because 0.5 is not in that interval. Okay, so it really depends if 0.5 is in the interval or not. And then studies have shown foods rich in compounds known as flavonoids help lower blood pressure. Investigate whether greater blood pressure reduction in blood pressure for people who consume dark chocolate, which contains flavonoids. Okay, than people who consumed white chocolate, which does not. 25 healthy adults agreed to participate and add 3.5 ounces of chocolate to their daily diets. 25, 13 were dark chocolate group, rest were white chocolate. Okay, all participants had their blood pressure recorded in millimeters of mercury before adding chocolate to their diets and gaining again 30 days after. Okay, so this is the reduction before minus after. So compare the medians. So find that middle dot, probably somewhere around here, and find this middle dot, which is probably right here at this one of these -2s. Oh no, this is 12 people, so it's actually going to average out to 0. Okay, and over here it's going to be somewhere over here. It's going to be the 7th dot. So right there, about 7. Okay, compare the medians. So we have the two medians. Make sure you use a comparison word like the median reduction in blood pressure for the dark chocolate group was 7 mmHg, which is greater than the median reduction in blood pressure for the white chocolate group, which was only 0 mmHg. Okay. Then the researchers found the mean reduction in blood pressure, X bar dark, X bar white. One researcher indicated that because of the difference is 5.66 is greater than 0, there's convincing statistical evidence. Why might the researcher's conclusion based only on the difference in sample means not necessarily be true? Oh, because this is evidence that it's greater than 0 because we didn't get exactly 0. So any non-zero number is evidence that it's not 0. But could it still be 0? And this is where you would need a p-value. Why might the researcher's conclusion based only on the difference not necessarily be true? Because if you have really big standard deviations, okay, then when you add those variances, and because we have small sample sizes, then it may only be one standard deviation away from 5.66 to actually get to 0, in which case it's not that unusual. That happens 68% of the time you're within one standard deviation, okay? And so it's only 32% of the time that you're one standard deviation away or more, okay? So there could be a wide distribution, could be because there's a small sample size in both the two groups that this might, even though it's evidence, it might not be statistically significant, convincing evidence, okay? And then here's a simulation. Whether there's a greater reduction in blood pressure for those who consume dark chocolate. The simulation was done many times, assuming that the null is true, that no difference exists, okay? Here's 120 simulations, and using this result, okay, the simulation determined whether results from 25% participants at a 5% level of significance that adding will result in a greater reduction in blood pressure than adding white chocolate, okay? So here's the simulated differences in means. We got 5.66. So we want to count how many dots are above 5.66, and it looks like 3 out of 120, which is 1 out of 40, which is going to be a really small probability, okay? We're looking at about 2.5%, all right? So it is less than 5% chance according to this simulated data, assuming that the null is true. So yes, it seems convincing based on that. And then we get here, question 6. To compare success rates for treating allergies at 2 clinics that specialize in treating allergy sufferers. Researchers selected random samples of patients' records from the 2 clinics. The following table summarizes the data. Unsuccessful treatment at Clinic A, Clinic B, successful Clinic A, Clinic B. Okay? Complete the following table by recording the relative frequencies of successful and unsuccessful treatments at each clinic. So Clinic A is 51 out of 139 and 88 out of 139, Clinic A, and Clinic B is 33 out of 68 and 35 out of 68. So this is almost 50-50, whereas this one is much less, okay? Based on the relative frequency table in parts A through AI, which clinic is more successful? So successful, this is just over 50% of the time. This one is well over 50% of the time. So clinic A is the one that seems to be more successful, okay? Based on the design, would a statistically significant result allow the researchers to conclude that receiving treatments at the clinic you selected in Part A causes a higher percentage? Well, that depends on whether or not they were randomly assigned to the two clinics. So now I'm going back to read this, okay? Researchers selected random samples of patient records from the two clinics, right? We're not randomly assigning them to the two clinics, so we cannot conclude causation. We can only assume or conclude that there is a correlation or an association, okay? So no, because it was not random assignment to the two clinics. And then a physician who worked at both clinics believed that it was important to separate patients in the study by severity of their allergies, severe or mild. The physician constructed the following Mosaic plot. The values in the Mosaic plot represent the number of patients who were either successfully treated or unsuccessfully treated in each allergy severity group. For example, the 78 represents the number of patients successfully treated in the mild group within Clinic A. Okay, so you look at this, and it says, based on the Mosaic plot, the physician concluded the following. For mild allergy sufferers, Clinic B was more successful. So for mild, Clinic B, because it was 11 out of 12. But for severe, Clinic B was more successful. Look at that. It's like 85, 90%, or 90, more than 90% right there. More than 40%. This one's less than 80. This one's less than 30. That's crazy, okay? For each clinic, which allergy severity is treated more successfully? Justify your answer. So Clinic A, if you do 78 out of that, or you can just estimate the percentages, but with the numbers here, I would actually calculate 10 out of 35, 78 out of whatever those add up to, 24 out of those, and 11 out of 12, okay? And which ones treated more successfully? They both are better at mild, better at mild, better at mild, okay? Clinic A is better at mild. You can tell by the way higher bar and the lower bar, way higher bar, way lower bar, okay? But then it's got to ask me about what's called Simpson's paradox. Which allergy is more likely to be treated? Okay, so at Clinic A, if you look at this width, we're far more likely to be dealing with this. So this would be that sum out of the total. And here we're only looking at 12 out of the total, okay? So why does Clinic B do both and better? Because this is a ridiculously small sample size, okay? And so it seems like it's a higher percentage, but really the one that they do poorly, or like the less severe ones, are not providing as much data, okay? So Clinic A, more likely to be treating the mild. Clinic B is more likely to be treating the severe, okay? And so using your answers from Part C, give a reasonable explanation why the more successful clinic identified in Part A is the same as or different from the conclusions in Part B. So in Part A, we said, who was the best? We said it was Clinic A was doing better. But here we're realizing Clinic B is better in both cases. So which one's actually better, right? Because we're saying which one's better in Part A. And using these answers from Part C, which one seems better? It seems like Clinic B is better. Okay, this is the idea of Simpson's paradox, that the overall percentages might look better here, but really, this group, the reason why their overall percentage looks bad is because the majority of the things they treat are the severe treatments, but they're up above 40%, where they're only at like 30% in the severe. It's because they get so many mild people to drag their overall percentage up that they look better overall compared to Clinic B, okay? So I would say Clinic B looks overall more successful. And I reached the end. Don't know how long that was, but I hope it was helpful. So good luck and farewell.